Hey guys, welcome back to another video. In this video, we're going to solve a few hard questions from the topic oscillation, that is from A2 physics. And I've sorted around 5 questions for this video. And I've also made the full playlist for oscillation chapter that is available on my channel. And we're going to start off with the first question that is from 9702, summer 18 and paper 4-1, right? First question, and this is, by the way, question 2 of this paper. So you can try it on your own. So starting off with the question, a metal plate is made to vibrate vertically by means of an oscillator as shown in figure 2.1. So you have a bunch of sand particles placed on a plate that is being vibrated by the oscillator. So these sand particles are going to move up and down. Now you can relate this with those videos online where you'll see a bunch of sand particles being placed on a sound box, and the moment you play a music, the sand particles are going to vibrate, right? They're going to bounce up and down. So what you can notice over there is oscillation is taking place. Now in this case, a specific type of oscillation you'll see that is simple harmonic motion. What is the formula of simple harmonic motion, mind you? Acceleration is proportional to negative of displacement, right? Fair enough. If you remove the proportionality, it's going to be acceleration is equals to minus omega squared x. Now, the question is telling you some sand is sprinkled onto the plate, or they didn't say that. Never mind. So, the variation with displacement y of the acceleration a of the sand on the plate is shown in figure 2.2. So let's analyze the graph. Through the graph, you can see while the displacement is negative, so let's say the displacement of this sand particle is downwards, right? Is downwards. At that point, the acceleration of the sand particles is actually upwards, right? So the oscillator is vibrating or moving the sand particles in such a way that the acceleration of the sand particles are opposite to the displacement of the sand particles. Now, the moment you see this, what can you say? Simple harmonic motion is taking place. Why? Because acceleration is proportional to x, that is displacement, because you can see a straight line going through origin. The second thing is, acceleration is in the opposite direction compared to displacement, because when the acceleration is positive, your displacement is negative. Those two things you're going to keep in mind. And while answering a part 1, that is show that it can be deduced that the sand is undergoing simple harmonic motion, those two things you're going to talk about, that acceleration is proportional to displacement and the gradient of this graph is negative. Hence, acceleration is opposite to the displacement. Okay, so those two things you're going to talk about in this question and you'll get 2 marks. Fair enough. Now, going to the part 2 of this question. Calculate the frequency of oscillation of the sand. Great. Now, what can you do over here? What do you know about angular frequency, the formula? Omega is either 2 pi by t, or you can substitute 1 by t as frequency, and you can say omega is 2 pi f. Great. So, I can form an equation from this. How? So, I can input this into this formula, right? So, let's do that. And we're going to be left with 2 pi f whole squared times x. So it's supposed to be y actually, because they're representing displacement as y. So I'm going to write it as y minus over here and equals to my acceleration a. Great. Now, the real question is, how do I find out this frequency? The easy way to do it is find your value of y, find your value of acceleration, and make frequency the subject. How do you do that? Use the values from the graph, right? So what two values can I take over here? I can take acceleration as 4.5. This is exactly 4.5, positive 4.5. I can take the displacement as negative 8 because at this point, the displacement is negative 8. So let's take those two values and try finding our frequency. So what did we see? 2 pi f whole square times 8. By the way, this is millimeters, right? So you have to turn it into meters. So you're going to multiply with 10 to the power minus 3 because you're converting it to meters. 10 to the power minus 3, right, is equals to acceleration, which we saw was 4.5. 4.5. Now, over here, it's nothing but making frequency the subject. So if you make frequency the subject over here, what you're going to see is your final value of frequency is 3.775 and you're going to write your final answer as 3.8, right? Great. So that is basically it for A part 2. So you can try it for yourself. You can make frequency the subject and see if your final answer is 3.8, right? Those two, considerably easy. So now moving on to question B or part B. What is it saying? The amplitude of the oscillation of the plate is gradually increased beyond 8 millimeters. The frequency is constant. At one amplitude, the sand is seen to lose contact with the plate. For the plates, when the sand first loses contact, what is the position of plate? So what they're telling you is they're increasing the amplitude. They're increasing the amplitude. So if I look at the graph, what can I understand? If I increase the amplitude, my acceleration also increases. My acceleration also increases, but in the opposite direction. If my acceleration increases, what do I know from F is equals to ma? Acceleration increases means net force increases. Great. So if I'm increasing the amplitude, I'm increasing the acceleration. So if I'm increasing the acceleration, I'm also increasing the force. Great. Now, the other thing they mentioned is the frequency is constant. So from W is equals to 2 pi f. Angular frequency is 2 pi f. If your frequency is constant, your angular frequency is also constant. So keep that in mind as well. Now, let's understand where, at what position will it first lose contact with the plate? Where, at what position, the sand will lose contact with the plate? Notice one thing, considering this, the equilibrium position, over here, you know, V is max. Maximum velocity is seen over here. Why? Because at this position, acceleration is 0. Where is acceleration maximum though? At this point and at this point. At the topmost position and the bottommost position. Right? Fair enough. So at this position, what is your normal acceleration? That means in this case, there is negative 4.4. Negative 4.4 meter per second squared. That is the acceleration, negative 4.4 meter per second squared is the acceleration of what? Of the sand. And at the bottommost position, the acceleration of the sand is 4.4 meter per second square of the sand. Now let me ask you a question. At the topmost position, if you analyze the situation of the sand, these are your sand particles. The weight acting on sand in this position is downwards, right? So sand will have a acceleration downwards due to its weight. But we know gravity is 9.81. That should be downwards. However, our acceleration is 4.4 meter per second square. That means the plate, even at this position, is exerting some amount of force upwards. That is, some amount of force on the sand upwards is being exerted by the plate on the sand, such that the net force is downwards but only resulting in 4.4 meter per second square of acceleration downwards. Therefore, we can understand that if I increase the acceleration or increase the displacement of the plates, what will happen? The acceleration of sand will actually increase. The reason behind that is, as you increase the displacement, notice the acceleration of the sand particles are supposed to increase because the plate will stop exerting force at the topmost position, such that it reaches 9.81 meter per second square of acceleration, such that the acceleration of the sand particles are downwards and the plate doesn't exert any force on the sand. Therefore, at the topmost position, when you reach an amplitude where the plate stops exerting any force on the sand particles will lose contact with the plate. However, the same can't be said with this lowest position. Notice one thing. At the lowest position, if you place a bit of sand over here, notice the weight is acting downwards, but the plate is pulling it upwards. Therefore, at this position, the sand, no matter what you do, is not going to lose contact because A, the plate is pulling the sand up and the sand is pulling itself down. So it's not going to lose contact with the plate. However, at the topmost position, when you have increased your amplitude and your acceleration is maximum, that is 9.81 meter per second, that is due to gravity, that means your plate has stopped exerting a force on the sand upwards, which is why at that position, the sand will not be in contact with the plate. It will fall on its own due to gravity, right? Fair enough. So we can understand from this situation that when your your displacement is maximum at that position, that is positive displacement, at that position, you're going to see the sand particles will lose contact with the plate because the plate stops exerting any force on the sand particles. So understanding this, all of this is very crucial for answering the next part of this question. So you're going to say in this part 1 of B that at amplitude or at max displacement, the sand particles will lose contact with the plate, right? It's going to lose contact with the plate. Fair enough. So hopefully you understand why it's going to lose contact, because plate stops exerting any force and the sand particles are going to fall on its own due to gravity, 9.81. Now, the next question is asking you, calculate this amplitude. This amplitude at which the sand particles lose contact. So, as mentioned over here, when your acceleration is going to be 9.81, that is of the sand particles, in that case only the sand particles will lose contact with the plate. Therefore, I can say if that is force on the this is force on the sand is mg, that is weight of the sand particles, is going to be equal to ma, that is your mass times acceleration. What this means is when the net amount of force on the sand particle is only its weight, only in that position will the plate lose contact with the sand particles. Therefore, I can say mg is equals to mass times acceleration. M and n is going to be cancelled off. So g is supposed to be the acceleration. As mentioned above, when the acceleration is 9.81, that is gravity, only in that case the sand particles lose contact, right? Therefore, I can say acceleration is supposed to be a. Now, I can also say from this equation, omega is equals to minus, acceleration is omega square times x. So I can substitute this value instead of, this expression instead of acceleration, right? So if I do that, I'm going to get g is equals to omega squared times x naught. You know the omega doesn't change. Why do you know that? Because frequency is constant. So you know for acceleration to be 9.81, this is your omega square value, and you're going to find out at what amplitude it's going to take place. So now when you make x naught, it's supposed to be y naught actually. They're representing amplitude as y or displacement as y. So write y naught. And now make y naught the subject. You know frequency from above, I guess 3.8 or something. Yeah, 3.8. 2 pi constant. 9.81 you know. And now make y naught the subject. And you're going to find the amplitude of the plate. The maximum displacement of the plate at which this is going to take place. At which the particles or sand particles are going to lose contact with the plate. Now mind you, at this position, at max position and at lowest position, in both cases, the acceleration is going to be 9.81. In the topmost position, it's going to be due to the weight of the particles. At the lowest position, it's going to be due to your plate pulling your sand particles up. So it's going to exert a force upwards on the sand particles, right? So that is why in both cases, you're going to see acceleration of 9.81. But it's only going to lose contact in the topmost position where the force exerted by the plate is 0. Hence, no contact between the sand particles and plate, right? So this was a pretty conceptual question. And if you had good idea of how oscillations or, simple harmonic motions work, where acceleration is 0, where is, velocity maximum, and at which position or due to what factors the net force can act. Can it be weight? Can it be the oscillator itself? What factors or what is the net force of any oscillating object at any position? You need to be able to analyze that, because we had to understand what the net force or what the total amount of force at any position was, right? So keep a clear idea of oscillation and why acceleration is maximum, minimum, or 0, right? So fair enough. That was question 1. Now question 2. So this question is from WIT 22, paper 4.1, and this is question 3 of that paper. So what is the question saying? An object is suspended from a spring that is attached to a fixed point as shown. Right. So fixed point, spring, object oscillates about this point, sorry. Right? Due to the spring. Great. The object oscillates vertically with simple harmonic motion about its equilibrium position. This is the equilibrium position. It moves up, it moves down. Great. State the defining equation for simple harmonic motion. Identify the meaning of each of the symbols used to represent the physical quantities. So they're telling you if a is equals to minus omega square x, what are these quantities? Define them and you're going to secure 2 marks. Great. Also tell that acceleration is opposite but proportional to the displacement. Great. So if you tell all of that, you're going to get 2 marks. Now, part B, the variation with displacement x from the equilibrium position of the velocity of the object is shown, right? So it's showing you how is the velocity going to vary. So even without looking at the graph, you can tell at equilibrium position, it's going to be maximum velocity, right? At equilibrium position, max velocity, max kinetic energy. At topmost position, it's going to have the maximum amount of potential energy. However, 0 kinetic energy, right? Fair enough. So moving on with the notion. At the topmost position, the velocity is also 0 because kinetic energy is 0. So moving on with that, at displacement is equals to maximum above, it's going to have a V 0. Maximum below, V is equals to 0 again. At the middle position, your velocity is maximum, 0.2 meter per second. Great. Which is why it's an ellipse, right? And you know the formula of velocity, by the way. V is equals to omega times root over amplitude square minus your displacement square. It's supposed to be this. Anyways, so let's move on with the question. The variation x of the potential energy, EP of the oscillation of the object is shown. They're telling you at lowest displacement, maximum potential energy. At maximum displacement, maximum potential energy. Now, what usually you would see is, or would understand is, at maximum position, it's supposed to have the maximum potential energy, and at the lowest position, it's supposed to have the lowest potential energy if you're talking with respect to gravity, right? But this is with respect to the potential energy inside the spring, right? So you have to consider the potential energy inside the spring. So understand that from this position to this position, from equilibrium to max position, you're going to contract the spring, which is why it's going to store potential energy inside the spring. And when you move below the equilibrium, you're stretching the spring. So you store energy inside the spring again. Fair enough. So it shows you at max displacement on either end of, that is below or above the equilibrium, you're going to see maximum amount of energy stored. And at equilibrium, 0. Great. Now figure 3.2 and figure 3.3 determine the amplitude. You can determine from over here, maximum displacement is at this position. So 0.12 is your amplitude. 0.12 is your amplitude. Part 2, show that the angular frequency of the oscillation is 1.7 rad per second square. So what you can do is basically use this equation. How? So let's say you want to find out, you know the velocity. Where do you know the velocity? Let's say at this position, when your displacement is 0, let's say I know the velocity to be 0.2 meter per second, right? So let's work with that. V, I know is 0.2 when omega is always constant. So I'm going to find out omega times root over of x naught square, which I know to be is how much? 0.12 meters. 0.12 square minus 0 square. Why? Because at this position, when velocity is maximum, remember your displacement is 0. So minus 0 square. So when I simplify, it turns out to be omega times 0.12 because root and square cancel off. So your omega is going to be 0.2 divided by 0.12. And your final answer turns out to be 1.7. Great. So your final answer is 1.7 rad per second. Now part 3 is asking you determine the mass of the object. How do you find the mass of the object? Easy. So you know that the total energy formula in any case is half m a square times v square, omega square. So that is basically from half mv square, that is at maximum kinetic energy. That is also going to be your total energy, because at this point it's going to be the same amount of energy but stored as potential energy instead of kinetic energy. At the again lowest position, it's again stored as potential energy instead of kinetic energy. Kinetic energy is 0. And at middle ground, at the middle equilibrium position, maximum kinetic energy. So energy stored as kinetic energy, no potential energy. Therefore, total energy is always constant, right? It's always constant. So with respect to any formula, you can find out the total energy. So I'm considering the kinetic energy formula for maximum velocity such that I find out the total energy. So when I know Vmax, that is also the total energy, because energy is conserved through the entire motion, right? Fair enough. Okay, so V square, I'm substituting as amplitude times omega square. So I know the amplitude, I need to find out the mass, I know the angular frequency, I also know the total energy, right? How much is the total energy? You know from this graph, 0.05 joules. So 0.05, plug in the value of amplitude, which is 0.12. What is your omega? 1.7. Now make mass the subject and your final answer turns out to be 2.5 kg. Great. Now moving on to part C, what is it saying? The oscillations of the object are now lightly damped. What is the meaning of damping? Damping means loss of energy of the system due to resistive forces. So when there are any sort of resistive forces, it's going to cause loss of energy, because energy may be lost as heat or any other conversion of energy. So usually it's heat, which is why resistive forces, it's going to take out energy out of the system, which is why it's going to start oscillating with a lower amplitude. So amplitude decreases, meaning energy is being lost, right? So loss of energy due to resistive forces. Great. C part 1. C part 2. Assume that damping does not change the angular frequency of the oscillation. On figure 3.2, sketch the variation with x of v when the amplitude of the oscillation is 0.06 meters. So they're telling you the amplitude has decreased to a value of 0.06. Great. I know that my angular frequency has not changed. It is constant. So let's find out for when displacement is 0. Because I know when displacement is 0, my velocity is maximum. So I can plot that easily. So I can also substitute this x as 0. So it makes it easier for me. So v is equals to omega, which is constant, times, remember, my x naught value initially was 0.12 meters. Now it is what? 0.06. So the value has become times half. Therefore, I can write it as x naught, I can write it as half times x naught. So half times the initial value squared. Great. So now when this root over is going to be above the square value, both are going to be cancelled off, right? So v, you're going to be left with v is equals to omega times half x naught. Therefore, notice your velocity, maximum velocity, has actually halved in value. So if your amplitude has halved in value, your velocity will also halve in value. That is your maximum velocity. Therefore, I can say if your maximum displacement or amplitude is 0.06, your maximum velocity will be 0.1. Why? Initially it was 0.2. So if your velocity is halved, it's now going to be 0.1 because your amplitude is halved. And we saw by deriving that if you halve your amplitude, your maximum velocity also gets halved. So easily you can plot the 4 points, that is 0.06, 0.06, which was given, and 0.1, which you figured out by saying velocity will be halved. You said 0.02 times half. So 0.01. Great. So you plotted these 4 points and now draw a circle, or ellipse, joining all 4 points. That is going to be your answer. Great. That was question 2. Now moving on to question 3. The mass m is now suspended from 2 springs, each identical to that in figure 3.1 as shown. Now the thing is, this is a continuation to another question, right? So what that question was saying initially what the question was is there was one spring attached to one mass, right? And that spring was of length L. Great. Now this spring was pulling the entirety of this mass, right? So this oscillation was taking place with respect to one spring pulling a mass of m. Now the situation has changed. Now they've changed the situation into bringing in 2 identical springs. 2 same springs are pulling the same mass m. Therefore, each spring is pulling half m. So this spring is pulling half of m. This spring is also pulling half of m. Great. So 2 springs are now pulling the same amount of mass. Now the question they're asking is, suggest and explain the change, if any, in the period of oscillation of the mass. A numerical answer is not required. To prove this, by the way, I will show you a derivation. You can easily say that since there is greater amount of pulling force, that is restoring force, since there are 2 springs right now, your period is going to be shorter, right? Because now 2 springs, identical springs, are pulling the same amount of mass, which is why period is going to be shorter. You can easily answer it that way, but I'm going to show you a small derivation such that you can prove it mathematically as well. Now, you know, in each of those cases, initial case where F is equals to ma, right? You know the acceleration to be what? You can write the acceleration as r times omega square, right? your R is going to be your that is your displacement, right? R is going to be your displacement, and your omega is going to be your angular frequency. Fair enough. Now with F is equals to ma, when you substitute this expression into acceleration, you're left with F is equals to m times R times, okay, there's no space over here, so I'll write it. F is equals to m times R times angular frequency squared. So when you break angular frequency down to get a formula of time period, you will see that F is equals to m times R times 2 pi by t whole square, right? Fair enough. Now, what you're going to see is, in case of these two springs, since you bring in two springs, with respect to one spring, it's only pulling a mass of m by 2, half m. So with respect to one spring over here, if I want to find its own time period, what I'm going to see is F is equals to ma, same formula. F is equals to m by 2 times R times your 2 pi by t whole square, which is your acceleration. This is your acceleration. Now notice one thing. I can also write the force as kx. I can write the force to be kx. Why? Because the restoring force of each spring is actually this constant times the displacement. So greater the displacement, greater the pulling force. You know it from probably AS level, this formula. So if you substitute this value over here, you're going to notice kx is equals to m times R times 4 pi square divided by time period square. If you make time period the subject, what you're going to see is m times R times 4 pi square divided by it's going to be kx, right? Fair enough. Now this x, by the way, this x is basically displacement, so I can write the x as R, because initially I wrote the x as R over here, so I can write the x as R as well. Doesn't matter, it's the same thing. So I can cancel both the r's out, this r and this r, and you're going to be left with t square is equals to m times 4 pi square divided by k. So take the 4 pi square out, and you're going to be left with, if you take a root on either side and try to make only t the subject, you're going to be left with 2 pi root over m by k, because root over 4 pi square is going to be 2 pi, right? So this is your time period equation for initial case where you're dealing with the entire mass. So one spring is dealing with the entire mass. In the new case, what's happening is one spring is only dealing with half the mass. Now on this side of the equation, what you're going to see is, again, continuing with this equation where the spring is pulling only half the mass again, your force is going to be m by 2, because mass has been halved, times r times 2 pi by t, that is your omega. Fair enough. Now what happens when you make t squared the value, subject, you're going to be left with m by 2f, because I brought the f over here, times x times 4 pi square. Now if I input the f is equals to kx, then I will be left with half times m by kx times x times 4 pi square. Now the x and x, the r and r, I can cancel off, and I'll be left with t square is equals to half times m by k times 4 pi square. Great. Now when you take a root on either side, you'll be left with t is equals to root over 2 times pi times m by k. Now notice one thing, between this and this, in both cases, notice this portion of the equation is the same. The only variation is with the 2. Notice in the new case you have root 2, and in the previous case you had the whole number 2. What that means is your time period has decreased, because root 2 is definitely less than 2. That means your time period has decreased. So mathematically you can definitely prove the time period decreases when you add another spring, right? You could also simply answer with logic, right? Okay, Now moving on to the next question. A U-shaped tube contains some liquid. The liquid column in each half of the tube has length L as shown. The liquid columns are displaced vertically. The liquid then oscillates in the tube. The liquid levels are displaced from the equilibrium position as shown. The acceleration A of the liquid in the tube is related to the displacement x by expression A is equals to minus g by L times x, where g is the acceleration of free fall. So notice g by L over here is acting as omega square. Explain how the expression shows that liquid is in the tube is undergoing simple harmonic motion. Simply say that g by L is omega square while acceleration is proportional to the negative of displacement. Now part B, the length of each each liquid column is 18 centimeter. Rewrite it as 0.18 meters. Determine the period of the oscillation. Now what you know is g by L is omega square. You can write this omega square as what? 2 pi by t whole square, g by L. Now what? You know the value of gravity to be 9.81. The value of L is given 0.18. 2 pi constant. Time period you're going to find out. Make time period the subject and the answer you get is 0.85. Right? Great. So now for part C, what is the question saying? The oscillations of the liquid in the tube are damped. In any one complete cycle of the oscillations, the amplitude decreases by 6% of its value at the beginning of the oscillation. Determine the ratio between the energy of oscillation after 3 cycles, E after 3 cycle, and initial E. Right? So they're asking you that what will be the ratio between energy after 3 cycle and initial energy. However, the decrease they've given is in terms of amplitude, right? So I have to figure out how to relate amplitude and energy. Now before doing that, let's understand what decrease in 6% means. So if you have 100% of something, it decreases by 6% and becomes 94%. Now again, a 6% decrease of this is going to be 94 minus 94 times 6 by 100, right? So again, a 6% decrease of 94, right? Now the easier way to say this is my original value of, let's say I have amplitude of 1 meters, it's going to now become and decrease to 94% of the original value because the decrease is 6%. So what is 100 minus 6? It is going to be 94%, right? So you have 1 meters of amplitude, it turns or becomes 0.94 A. 0.94 A. After another oscillation, it further decreases to more 0.94% of this value. So by the second oscillation, again you multiply 0.94 because of this amplitude, it will decrease to 0.94 or 94%. So again, by the third ratio, what happens? By the third ratio, what's going to happen is you're going to multiply the 0.94 once again because of this value of second oscillation. This amplitude decreases again by 0.94 by a factor of 0.94. 0.94. So I can simply write that the decrease in amplitude after 3 oscillation is 0.94 to the power of 3 times amplitude. This is the decrease in amplitude. How much the amplitude will decrease compared to my initial amplitude. Now, an easier way to understand this is by thinking with respect to increase of something. So if you have amplitude of 1 and if they're saying after each oscillation the amplitude increases twice, that means you're going to have after 1 oscillation 2 meters, after 2 oscillation you're going to multiply again with 2, 4, that's going to be 4, again after 3 oscillation again multiply 2, it's going to be 8, right? So what you see over here is the initial value times 2 to the power of 3. Number of oscillation is the power and my value over here 2 is going to be what? Is going to be the factor by which the value is decreasing or increasing. So you know from the question that since it is a decrease of 6%, it is becoming 94% of its original value. So how many times is it happening? 3 times. So 0.94 to the power of 3, or you can write it as 94 divided by 100, 94% to the power of 3 times your initial amplitude A. Great. So that is my variation of amplitude after 3 oscillations. So I know what's going to happen to the oscillation after 3 oscillations. So if your amplitude becomes 94% to the power of 3 times A after 3 oscillation, what is your energy change going to be? Let's figure that out. Now, you know the formula of energy, by the way. Your energy formula is actually given by half times mass times amplitude squared times omega squared, right? So you know that the energy is going to be proportional to your amplitude square. Because notice one thing over here, your mass doesn't change, your omega doesn't also change, and half is a constant, which means your energy is directly proportional to the square of amplitude. So we have to work with that idea, right? So when my energy was initial, the initial value E1, my amplitude was also A1 whole square. Now my new energy after 3 cycle, E2, is going to be 0.94 to the power of 3 times A1. Wait a minute. Okay. A1, right? To the power of 2. So carefully try to understand this ratio. What's happening over here? You know E1 is proportional to the initial amplitude square. Now my new energy after 3 oscillation is also proportional to its amplitude square. And what is the amplitude, mind you? It is 0.94 cube times A1. This is my amplitude, because the amplitude has decreased by a factor of 0.94 thrice. And this value you're going to square in the numerator to show that energy is proportional to the square of amplitude. Therefore, I can further simplify this to say that I can cancel the A1 and A1 off to be left with 0.94 to the power of 3. So my ratio between new energy after 3 cycle divided by your initial energy is going to be 0.94 to the power of 3. And if you calculate this out, it's going to be 0.69. Right? Phenomenal number and phenomenal answer. So that is going to be how you solve a ratio problem. You're going to find the proportionality between two variables and form a ratio between those two. Initial values, final values. Form a ratio and you're going to find the value, right? Great. So that is your question 4. Now moving on to question 5. This is not exactly a hard question, but I feel like I should add this bit of information. So I'm basically talking about this part, but let's start off with the first 10A. I don't know which year this is, I just added. So it's asking, explain what is meant by natural frequency of vibration of a system. What is it? The frequency at which an object will oscillate in without having an external force acting. That is, if you have a spring and you press it down and you release and you no longer exert any force on it, the frequency at which the spring will move up and down is its natural frequency. Therefore, the frequency at which an object will oscillate on its own without having any external force acting on it, that is the natural frequency. Great. Now part B, it's saying a block of metal is fixed to one end of a vertical spring. The other end of the spring is attached to an oscillator as shown in figure 4.1, great, oscillator, spring, and your metal block. Fair enough. The amplitude of oscillation of the oscillator is constant. Great. The variation of the amplitude of the oscillations of the block with frequency f of the oscillations is shown. Therefore, they're telling you the amplitude at which this oscillator is going to move up and down is constant. However, what is varying though is the frequency of this oscillator, the frequency at which it moves up and down. The frequency is changing, not the amplitude of the oscillator. Now, the amplitude or displacement of this metal block is plotted against the variation in frequency of this oscillator. So, with change in frequency of this oscillator, how will the amplitude x naught of the metal block movement change? That is what is plotted over here, right? Okay, so now the question is asking you, name the effect shown in figure 4.1. What is shown over here? Resonance. Resonance is taking place at this point, over here, where the peak is seen. That means the oscillator is vibrating at a frequency exactly same to the natural frequency of this spring. Fair enough. So we see resonance. State and explain whether the block is undergoing damped oscillation. This is what I wanted to share, that I basically didn't know this, but since over here, notice the peak is not as sharp. Now, when you're studying it, you'll see that in the textbooks or in the diagrams, the peak over there is quite sharp, right? There's a sharp peak over here denoting one frequency at which max amplitude is seen, meaning at that frequency, resonance is seen. Now, the point over here is, since the peak is not sharp, it is going to go through damped oscillation. Why? This energy is not max at one position. Notice at this position, at this frequency, even though you see a peak, the peak is not as sharp because the energy has decreased. That means amplitude has decreased, which is why the peak you don't see to be as sharp, which is why you can deduce there is damping taking place. There is some sort of frictional force or any external force which is not allowing it to have the maximum displacement or the maximum amplitude, which is why you would have seen a peak like that, right? Great. So that means it is going through damped oscillation. This part is not needed. And that is going to be it for this video, and see you in the next one.